So the last thing that I want to introduce here is the inner product of two vectors in Rn. So by definition, the inner product of two vectors v and w in Rn is defined notationally with this bracket notation. So we'll write bracket v comma w close bracket. And what we're doing here is we're taking the corresponding coordinates of each vector, multiplying them together, and then adding everything up. So if the we'll take the first coordinate of v and the first coordinate of w, multiply those together. Then we'll take the second coordinate of v and the second coordinate of w, multiply those together, and we'll keep doing that until we get to the last coordinate of v and the last coordinate of w, multiply those together, and then we add everything up. This is also called the dot product of two vectors. I'm going to use the term inner product in the notation for inner products, but it's extremely common to see this called the dot product. So that's sometimes written as v dot w. I just sort of prefer this language of inner products. So let's look at an example. So here we have two vectors, and they're both in R4, so they both have 4 coordinates. How do we take the inner product of these two vectors? Well, according to the formula, I simply compare the corresponding coordinates, multiply them together, and add everything up. So we should have 4 terms. The first term should be the first coordinate of v multiplied by the first coordinate of w. The second term should be the second coordinate of v multiplied by the second coordinate of w. The third term should be the third coordinate of v multiplied by the third coordinate of w. And the last term should be the fourth coordinate of v multiplied by the fourth coordinate of w. When we do the multiplication here, what is it? 3 times negative 7 is negative 21. 1 times 0 is 0. 2 times 3 is 6. And let's see here. Negative 2 times negative 9. I suppose that's a typo here. I guess this should be plus 18. So let's see if that carried over. So I should end up with 6 plus 18 minus 21, which I guess is 3. So I guess I did the arithmetic right here. I just have a typo here. This minus should be a plus sign. I'll fix that. If I don't fix it, if it's out there when you look at the slides, somebody send me an email and I'll make a note to fix it. Now, one thing to point out here is that when we take the inner product of two vectors, we produce a scalar value. So whatever the inner product is, it's given by this silly formula. When we applied it to these two vectors, we ended up with the number 3. Now, warning, like with a lot of other constructs that we've developed, it only makes sense to take inner products of two vectors that have the same shape. So we might try to take an inner product of a vector with 2 coordinates and a vector with 3 coordinates, but that doesn't make any sense because those are different numbers. We might try to take an inner product of a vector with 4 coordinates and a vector with 6 coordinates, but that doesn't make any sense. So we can't do that because it doesn't fit our definition. We wouldn't know how to line up the coordinates appropriately. Do you line up like the first coordinates that you can match and then ignore all the other ones, or do you line up the last coordinates you can match? It doesn't make any sense. So what sorts of properties do inner products obey? The first property is the commutativity property. All this means is that it doesn't matter the order we do this in. The inner product of v with w is the same thing as the inner product of w with v. There's also a linearity properties. So the first property is called left linear. What this means is that if I have a linear combination of two vectors v1 and v2 in the first slot of an inner product, I can distribute the inner product across that linear combination while keeping my second vector fixed. So the inner product of c1 v1 plus c2 v2 with w is c1 multiplied by the inner product of v1 with w plus c2 multiplied by the inner product of v2 with w. There's also a right linear rule, which says if I'm taking the inner product of a vector v with a linear combination of vectors on the right-hand side, I can distribute the inner product over the linear combination. So v inner product with c1 w1 plus c2 w2 is the same thing as c1 times v inner product with w1 plus c2 times v inner product with w2. There's another famous formula which is called the adjoint formula. remember, we can take a matrix and multiply by a vector to produce a new vector. Well, let's say that I did that. Let's say I multiplied A times a vector V to produce a new vector, and then I decided to take an inner product of that new vector with some vector called W. It turns out that this is the same thing as taking the inner product of the original V before I multiplied by A, not with W, but with the transpose of A times W. This is kind of a cool formula. The way I like to think about this is that if you have a matrix inside of an inner product, the matrix can bounce back and forth like to either side, but every time you move it from one side to another, you have to transpose. So that's a cool property. There's also a length formula. Think about what it means to take the inner product of a vector with itself. Well, what you're doing is you're taking all of the corresponding coordinates of V with itself, multiplying them together and adding everything. So you're taking the first coordinate, squaring it, plus the second coordinate, squaring it, so on and so forth, and then you're adding everything up. That's the same thing you do when you find the length of a vector, except there's no square root in that process. So the inner product of a vector with itself is always equal to the length of that vector squared. This is where we're going to connect the idea of the silly arithmetic behind inner products with the geometry that we've been developing in this lecture. So I just want to go through maybe like a sort of homework type problem to acquaint ourselves with what it's like to work with inner products. So let's say I'm in a situation where these three conditions are met. Let's say that I happen to know that the inner product of a vector v1 with a multiplied by a vector w2 equals -2. Let's also say that I happen to know that a multiplied by a vector w1 is 0, and a transpose multiplied by a vector v2 is 0. Let's now calculate a particular inner product. So here I'm going to calculate the inner product of 3 times v1 plus 7 times v2 with the vector obtained by taking a and multiplying by the quantity w1 minus 6 times w2. So I want to simplify this expression as much as I can using the information that I'm given up here. So what's the first step? Well, the first step says, let's take a closer look at the second vector we're taking in our inner product. We're multiplying a by w1 minus 6 times w2, but we happen to know a times w1 is 0, so when I distribute my a here, I kill the w1 and I'm left with -6 times a times w2. So that's kind of cool. By using the fact that a times w1 is 0, we've simplified our expression just a little bit. And now I'm staring at this expression and I realize there's an a on the right hand side. So there's an a inside of my inner product. And remember, the adjoint formula says a matrix can bounce around in an inner product, but every time you move it from one side to the other, you have to take a transpose. So let's go ahead and do that. Let's move a from the right side of this inner product to the left side. But when we do that, again, we have to transpose. So now I'm looking at a transpose multiplied by the quantity 3 times v1 plus 7 times v2. And another thing I happen to know in this problem is that a transpose times v2 is the 0 vector. So if I went to distribute a transpose across this linear combination of v1 and v2, I know that the second term will be killed because a transpose times v2 is the 0 vector. So that really just leaves me with 3 times a transpose times v1 in my inner product here. So now a transpose is on the left-hand side of this inner product. Let's send it back to the right-hand side, but when we send it back, we have to transpose, and the double transpose is equal to itself. So I move a transpose to the right-hand side, and I just get a. And the other thing I'm doing is I'm factoring my two scalars that I have out of the inner product. So 3 comes out of the inner product because it's on the left-hand side of the inner product, and -6 also factors out because it's on the right-hand side of this inner product. So now I'm left with 3 multiplied by -6, multiplied by the inner product of v1 with a times w2. But we're told in this problem that the inner product of v1 with a times w2 is -2. So I should get a -2 here. And when I multiply 3 times -6 times -2, what is that? -6 times -2 is 12. times 3 should be 36. So we've used the properties of inner products along with some of the information we're given in this problem to simplify our inner product calculation. Okay, so what we've seen now is that inner products are connected to the idea of lengths by the formula inner product of any vector with itself equals the length of that vector squared. This is an incredibly useful concept, and I want to apply it in an interesting situation here. So let's say that I start with two vectors, v and w, that are, and I display them like this, so they both start from the same tail. Well, what I want to do is I want to look at the length of the difference, v minus w squared. So how does v minus w fit into our figure here? Well, v minus w is the vector obtained by traveling against w, because we have negative w, and then with v. So v minus w fits in nicely in our figure here. And let's say that I wanted to calculate this length squared. Well, the length of any vector squared is the same thing as the inner product of that vector with itself. Again, this is an extremely common trick in math, so I want us to get used to it. I'm interested in v minus w length squared. So what I can do is I can take v minus w and inner product with v minus w. Now what I can do is I can use my distributive rules to expand this inner product. So here I'm expanding from the left. The inner product of v minus w with v minus w, well, let's keep the vector v minus w on the right, but distribute from the left. So this is now v comma v minus w minus w comma v minus w. And now we can take these two inner products and distribute on the right. V comma v minus w can be expanded. This becomes v inner product with v minus v inner product with w. And then here we're subtracting off w inner product with v minus w. So this becomes negative w inner product with v minus negative w inner product with w, so that becomes a plus. So now I have these four terms, but I can do a little bit more simplification here. The inner product of v with itself is the length of v squared, and the inner product of w with itself is the length of w squared. And also, I have negative v inner product w here, along with negative w inner product with v. Well, remember, v inner product w is the same as w inner product v, so I can combine those terms. So all of this simplifies to the length of v squared plus the length of w squared minus 2 times the inner product of these two vectors. So we've managed to sort of expand out the formula for the length of v minus w squared, and we got a new formula for it. So that's nice. But I want to say a little more here. I want to dig a little deeper. When I'm looking at this figure here, I can't help but think of a certain area of math. And if we were together in a classroom, I would say, what area of math are you thinking about? And one of you would say, well, I feel like I'm looking at a triangle, so I'm thinking about trigonometry. And I'd say, that's exactly what I'm thinking about. So I'm thinking about trigonometry as well. In trigonometry, we have this thing called the law of cosines, which is a generalization of the Pythagorean theorem. And what the law of cosines says is that if I'm interested in maybe a triangle, and one of the angles here is theta, I can relate the lengths of all three sides of this triangle by using the cosine of theta. Rigorously, what it says is that the square length of the opposite edge of the triangle is the same thing as the sum of the squares of the adjacent legs of that triangle. And if this were the Pythagorean theorem and that was a right angle, we'd stop there. But in general, if this isn't a right angle, we have to subtract off the 2 times the product of those two lengths of the adjacent edges multiplied by the cosine of theta. So on one hand, so we have two calculations here for the same thing. On one hand, we've calculated the length squared of v minus w using inner products. And on the other hand, we dug back way into, I don't know, like middle school or whatever, and we wrote down a formula for the length squared of v minus w in terms of the law of cosines. Well, one thing we could do here is we could set these expressions equal to themselves and simplify. So if length of v squared plus length of w squared minus 2 times this product is the same thing as length of v squared plus length of w squared minus 2 times this inner product. There's a lot of cancellation that happens. Length of v squared cancels with length of v squared. Length of w squared cancels with length of w squared. This negative 2 canceled with this negative 2, and we're left with a nice formula. This formula tells us that the inner product of v with w is the same thing as the product of the two lengths of those vectors, so the length of v multiplied by the length of w, multiplied by the cosine of the angle between these two vectors. This is incredible because what it means is if we're talking about two vectors that live in any dimension, we now have a formula that makes sense, and it tells us how to work with angles in high dimensions. So I want to state this as a theorem. The inner product of two vectors is always equal to the product of the lengths of those two vectors multiplied by the cosine of the angle between those two vectors. Another thing that pops out of this is the famous Cauchy-Schwarz inequality. Remember, cosine oscillates between -1 and 1, so its absolute value is never larger than 1. So if I took absolute values on both sides of this theorem, this would end up telling me that the absolute value of the dot product here, I've used that dot product notation, which is the same thing as the inner product, is always less than or equal to the product of the lengths of those two vectors. And this is because the absolute value of cosine is always between 0 and 1. So let's look at an example where this is useful. Let's say we were looking at the vectors 1, -3, 4, and 1, 1, 1. How could we find the cosine of the angle between these two vectors? Well, we could go back to our theorem and just solve for cosine. Cosine is the inner product of v with w divided by the product of the two lengths. Well, that's easy enough. We can take the inner product of 1, -3, 4 with 1, 1, 1, and then divide by the product of the lengths of these two vectors. If we're taking an inner product of any vector with a vector full of 1s, all we're really doing is adding those coordinates. So 1 plus -3 plus 4 happens to equal 2. And then what are the lengths of these vectors? Well, 1 plus 9 plus 16 is 26. So we have root 26 for the length of v. And 1 plus 1 plus 1 is 3. So we have the square root of 3 as our second factor in the denominator. So however these vectors look like in 3 space, the cosine of the angle between them is equal to 2 divided by root 26 times root 3. And again, if this were class, I would bring up how I hate it in like high school or whatever. Teachers get like mad if you leave radicals in the denominator. Who cares? Radicals denominator is like totally fine. I think it's great. Okay, so what can we conclude from all this? Well, something we can conclude is since the cosine of an angle tells us to a degree how large the angle is just by knowing the sign or the signature of cosine, or that's to say knowing whether or not it's positive or negative, we can classify all pairs of vectors. So any two vectors you give me are configured in one of the following 3 ways. The pair of vectors is either acute, which means that they form an angle that's less than pi over 2. And one way you can quickly figure this out is by taking an inner product of those two vectors and checking that you get a positive number. The two vectors might also be obtuse. This means that the angle between the two vectors is greater than pi over 2. And one way you can quickly check whether or not two vectors are obtuse is by taking their inner product and checking that you get a negative number. And the third, and by far most important configuration, is the notion of two vectors being orthogonal. So to say that two vectors are orthogonal means that the angle between them is equal to pi over 2. That's to say that the two vectors form a right angle. This is determined by the equation inner product equals 0. Orthogonal is a mathematician's term for perpendicular. Normally, I like to sort of shy away from pretentious terminology, but I can't help it. I'm a mathematician at heart. I like the term orthogonal, so we're going to use it. Orthogonal means perpendicular, and the way we check whether or not two things are orthogonal is by taking an inner product and verifying that we get 0. This is going to come up again and again and again throughout the semester. So here's an example. Here I have two vectors in R4. The first vector has coordinates 3, -2, 1, 4, and the second vector has coordinates 1, 1, 7, -2. When I take the inner product of these two vectors, I compare the corresponding coordinates, multiply them together, and add everything up, and in this case, I get 0. So whatever R4 looks like, these two vectors can be thought of as arrows sitting inside of 4 dimensions, and they're configured orthogonally. They form a right angle with one another. And we know this because their inner product is equal to 0. Okay, so the last thing I want to mention here is that the formula for inner products, or the dot product, allows us to reinterpret how we've constructed matrix vector products. And it's important that we're doing this now and not before, because the way we introduced matrix vector products was by thinking of matrix vector products as linear combinations of columns of the matrix we're using. So we knew this equation before we did this lecture. If we take this 4 by 2 matrix and multiply by this vector in R2, we produce a vector in R4. And the way we produce this vector is by taking 3 times the first column of our matrix minus 1 times the second column of our matrix and adding those two things together. I'd be remiss, though, if I didn't shed light on a different perspective involving inner products. One thing that you might notice is that if you take the inner product of the first row of our matrix with the vector v in question here, you get 3 times -5 plus -1 times -8. That actually equals -7. So that's the first coordinate of the output. If you take the inner product of the second row of A with the vector in question, that happens to equal 8. If you take an inner product of the third row of A with the vector in question, you get the number -3. And finally, if you take an inner product of the fourth row of A with the vector v in question, you end up with 9. So this will work for any matrix vector product. And the idea is that the ith coordinate of A multiplied by a vector is the inner product of the ith row of A with the vector v in question. So this is an alternate perspective on matrix vector products, which requires the language of inner products and doesn't invoke the idea of linear combinations. I wanted to introduce the concept in terms of linear combinations because linear combinations are incredibly prevalent in mathematics and often overlooked. So that's where I want our intuition to come from. But this is also another way to calculate matrix vector products. Okay, so that's all I want to say about inner products and all I want to say about geometry for the moment. Thanks for watching.